Hello there. Let's go ahead and talk about some zero and negative exponents today. But first, I want you to review the concept of an exponent, do these problems without a calculator, and then restart the video when you're done. Okay, so let's really quickly talk about what zero and exponents, negative exponents, would look like. Let's start with the idea that, say, 2 to the first. Oh, gotta select my tool. There we go. 2 to the first is just that anything to the first power is just equal to 2. Okay. And then we increase the exponent by 1, 2 squared. Well, exponents are just repetitive multiplication. In this first example, 2 to the first was equal to 2. Okay. And then 2 to the second equals 2 times 2. Okay. And then we got 2 to the third, which is equal to 2 times 2 times 2. That'll be 8. Sorry, this other one was 4. And then one more for good measure, 2 to the fourth is equal to 2 times 2 times 2 times 2. That equals 16. Now, the reason why I bring this up is because we look at the idea of exponents as repetitive multiplication, but when we get to a zero exponent, what does it mean to multiply by something 0 times? Does that mean the answer is 0? What about negative exponents? Say I had 2 to the negative first. Does that mean I multiply by something negative 1 times? Saying 2 to the 0 is 0 kind of makes sense. You know, if we're multiplying something together 0 times, don't we have 0 to begin with? But then we get to negative exponents. And we think, okay, what does it mean to take 2 and multiply it negative 1 times? You can't have a negative quantity of something. Negative quantities usually represent something like money, where you might be in debt. But you can't say have negative apples unless apples were the currency. So let's talk about it. I'm going to tell you that 2 to the 0 is not equal to 0. Let's look at how we multiply when we increase the exponent. 2 to the first to 2 to the second. The result is being multiplied by 2. Same as if we went from 2 to the second to 2 to the third. We're multiplying by 2. And one more time, if we go from 2 to the third to 2 to the fourth, we're multiplying by 2. So anytime we increase our exponent by 1, we are multiplying by 2. And you can do this with any number you want. 2 is just the base example I looked at because the numbers are more manageable once we start calculating. So we have to think, what happens if I reverse the process? Well, if I'm decreasing my exponent 1, then it would stand to reason that I'm dividing by 2. So I would think, okay, what's 2 divided by 2? It's equal to 1. Okay. Now, this, again, may be intuitive. Again, I'm taking 0 2's and multiplying them together. The intuition tells us, oh, that would be 0. But when we're thinking multiplication, an empty set of multiplication would always just be equal to 1, since anything times 1 is itself. And then what's more, we can repeat this process one more time by dividing by 2. And we get 1 divided by 2. Well, that's just 1/2. Pardon me. So now really quickly, one more example. If we did 2 to the negative 2, we're taking 1/2 and dividing by 2. That would be 1/4. Now notice that 1/4 is also 1 over 2 squared. So when we take negative exponents, the kind of rule is that we would say, okay, I've got a negative exponent. Since I have a better understanding of what it means to multiply repetitively when the exponent is positive, let's try to create this scenario where I'm repeating multiplication with a positive exponent. So with a negative exponent, I'm going to create a fraction, in which case I take this whole thing and move it to the denominator. And the exponent would then become positive. And now I can think about 2 times 2 is 4. And then if I'm creating a fraction, we put 1 in the numerator, because like we did with 2 to the 0, I've got nothing But again, when we're talking about multiplication, and now that we're talking about division, nothing in a multiplicative and division sense means that we put a 1 there. Okay. Now, one real quick caveat. Again, you can repeat this with any number. Of course, your results would be different, but the patterns would still hold. If I was if I was doing 3 to the power, I'd be multiplying by 3. I'd be dividing by 3, 4, so on and so forth. But let's talk about 0 to the 0. Now, there's some debate around this, but I feel strongly in my explanation, so I'm going to show it to you. What is 0 to the 0? Since I just told you something to the power of 0 equals 1, it would stand to reason that this would be equal to 1. But let's look at 0 as a base really quickly. What's 0 to the first? Well, that'd just be 0. Anything to the power of 1 is itself. And 0 squared. Well, we know that exponents are a repetitive multiplication, so 0 times 0 is 0. And 0 cubed, that's 0 times 0 times 0. That's 0, and so forth and so on. So, okay, 0 to the power of 0 is 0. But if we look at 0 being the exponent, 1 to the power of 0 is 1. 2 to the power of 0, we just saw, is 1. Through similar reasoning, 3 to the power of 0 would be equal to 1, and so forth and so on. So what we do have is two lines that contradict each other. So for this reason, we say 0 to the power of 0 is undefined. I'm going to often say that anything to the power of 0 is equal to 1. I usually mean this as anything but 0 to the power of 0 is equal to 1. The reason why I won't repeat this is because it'll get cumbersome. So let's just keep in mind 0 to the power of 0 is undefined. It's not possible to calculate this value. And that 2 to the power of 0 or 3 to the power of 0 is equal to 1. Even say a negative number, negative 1 to the power of 0. Now, there's an additional caveat we have to be aware of. You saw this in the opener, and it's when we have groupings. You had negative 4 squared. That equals 16 because it's negative 4 times negative 4. Negative times a negative equals a positive. But if we lose the parentheses and we just write negative 4 squared, now we're no longer squaring the negative. It's negative 4 times 4. So 4 times 4 is 16, and then we have the negative left over, so this is negative 16. This assumes that there would be parentheses around just the 4. And if you're going to type this into your calculator, that's what your calculator would assume as well. So when we talk about, say, negative 2 to the power of 0, if it's in groupings like this, then yes, the answer is 1. But if it's negative 2 to the power of 0, again, just the 2 is being taken to the power of 0, not the negative. So that would be 2 to the power of 0 is 1 with the negative left over, and that's negative 1. Okay, so let's look at some examples. So 9 to the negative 2. Anytime we're doing these problems, we're thinking, okay, I've got a negative exponent. I'm going to create a fraction. And as time goes on, examples will get more and more complicated. But for now, since we're starting in the simplest form, all I've got is this one base of 9 with an exponent of negative 2. So I'm going to move that to the denominator, and I'm going to make the exponent positive. And then what's left over in the numerator is just 1. And then we can simplify from there. That's 1 over 81. Okay, now we've got negative 3.6 to the power of 0. This is what I just got done talking about. We got a negative number to the power of 0, but the negative is in parentheses with it. So this is just equal to 1. So go ahead, give the you-dos a try, and then restart the video when you're ready to rejoin. All right, so let's talk about example 2. So now we're bringing variables into the problems. We're not just talking about numbers anymore. So we have 5a cubed b to the negative second. So again, we're approaching this as if we're creating a fraction. Because again, I got a negative exponent. And that whole entire thing, b to the negative second, will go to the bottom. Okay. Now 5 will have an exponent of 1, which is positive, and a has an exponent of 3. Those are both positive, so there's no reason to change those. So 5a cubed would remain in the numerator. And since I don't have anything to calculate, this would be my final answer. Now, sometimes you may get a problem where you have the exponent in the denominator, but it's already negative. So let's go ahead. Let's think about this again, still as we're creating a fraction. So now we can start to think about anytime the exponent is negative, we change the level of where it's at. This b to the negative second here was technically in a numerator if we look at this whole thing over 1. Okay. Now we have an exponent that's negative in the denominator. We move that to the numerator and make the exponent positive. Now, there is nothing to go in the denominator, so anytime there's an absence, we write 1. Now, I want to be clear about this. We're not switching the 1 from the numerator to the denominator, and you'll see that in future examples. Okay, but again, anything over its 1 is itself, so we can just write this as x to the power of 5. And again, we're done because we don't have anything to compute. All right, go ahead and give these examples a try. All right, these examples specifically, I think I'll go over on video because there's nuance to every single one of them. So this x to the negative ninth. Once again, we have a negative exponent, so we're going to create a fraction. We're going to move that x to the negative 9 to the denominator. It's going to become positive. And we got nothing left over in the numerator, so we're going to put 1. Okay. In this one, this is like the x 1 over x to the negative 5 in the previous problem. So we're going to write our fraction. We'll move that n to the negative 3 to the numerator. And we got nothing left over for the denominator, so we put a 1. And then we can simplify that to just be n cubed. Pardon me. Now, here we've got an example similar to the first one on the previous slide. We got 4c to the negative 3, b to the first. Remember, anytime we have an absence of an exponent, that's an exponent of 1. Because anything to the power of 1 is itself. So let's think about when we create our fraction, what's positive? What's already positive will stay where it's at. So 4 and b will remain in the numerator. And then c to the negative third, since that's a negative, will go to the denominator. And we're done. Now, here's an important one. So this is similar to the 1 over x to the negative 5. So this we said x to the power of 5. And then we put 1 in the denominator. And I've seen this before when I've taught this. People think, okay, we just switched the 1 to the denominator. But we didn't actually switch the 1. We wrote a 1 here because we had an absence of a denominator. And we can't divide by 0, so we put a 1. And that's what became x to the 5th. So when we create this fraction, we're going to put a to the negative 3 in the numerator, like we did in that problem. We're going to keep the 2 where it's at, because again, the 2 has a positive exponent of 1. In this problem, we still technically kept the 1 in the numerator because anything times 1 is itself. It's the same as if we had a 1 for an exponent. We don't usually write that out. So now that we have written this out, we have an absence of a denominator, we still put 1. Okay, and then we can simplify that to be just 2a cubed. And now the final problem, m squared is in the denominator, and that's positive. So I'm going to keep it where it's at. This n to the negative 5, I notice, is negative, so I'm a negative exponent, pardon me. So I'm going to put that in the bottom, and then absence of a numerator, I'm going to put a 1, and then we're done. All right, let's go ahead. What is the value of 3s cubed t to the negative 7 for s equals 2 and t equals negative 3? So this is just a straight substitution problem. Now, when I tackle these, there's a couple things you can do. You can substitute first and then simplify everything, or you can move things around, create positive exponents, and then substitute. I'm going to do that because when we're tackling these kinds of problems, again, it doesn't intuitively have any meaning to take a negative exponent because then we're taking something and multiplying it negative times, which really doesn't make any sense. Whereas if we make it positive, we have this process now of turning it into a positive exponent, and then we can do calculations from there. So 3s. So like I did with the other problems, I'm going to create a fraction. I've got 3 is to the first power, so that's a positive exponent. That'll stay in the numerator. S cubed, that's positive, so that'll stay in the numerator. But this t to the negative second, that'll move to the denominator, and the exponent will become positive. Now I can have actual calculations. So 2 goes in for s, so 3 times 2 cubed. And then we got negative 3 squared in the denominator. Make sure you put the negative 3 in parentheses. And then make sure, again, as always, order of operations. So we start with exponents. 2 cubed is 8. And at the same time, we have negative 3 times 2, negative 3 to the second. That'd be 9. And now we've got 3 times 8 is 24. Now what we have is a fraction that we can simplify. Let's go ahead and divide out a common factor of 3. And we get 8 over 3. And we're done. All right, go ahead and try these problems. Simplify as much as possible. And then when you're done, go ahead and do the exit ticket and make sure you turn that exit ticket in. Okay, so I'm going to actually go over this problem because there's some subtle nuances. Now we look at the first one and we think, okay, let's create a fraction like we always do. N to the negative fourth will go to the denominator, but w to the 0 is not positive, nor is it negative. But remember, that will just always simplify to 1. And anything times 1 is itself, so we just go ahead and put a 1 in the numerator, and now we're good to go and calculate. So 1 over n to the fourth, that'd be negative 2. So negative 2 to the fourth. I know negative 2 to the fourth is 16. So 1 over 16. And we didn't need to mess with the 5 because we had eliminated the w. All right, so let's talk about the second one. In our fraction, w to the second will remain in the denominator because that exponent is positive. We have n to the negative 1. That just becomes n to the first. I won't write the exponent, and then I'll put my 1 here. So 1 over 5 squared times n, which is negative 2. And again, order of operations, we do the 5 squared first. 25 times negative 2. And we get a negative 1 over 50 as our final answer. All right, next one. Again, n to the 0, that'll just simplify to 1. And w to the 6th just remains in the denominator. So we got 1 over w to the 6th. Then we plug in our 5. And I'm actually not going to do that calculation. I'll leave that up to you. But it's 1 over whatever this number is. And then finally, let's go ahead and create our fraction. We've got w to the negative 1 will move to the numerator, and n has a positive 1 as an exponent, so we'll keep that in the denominator. So w is 5, and n is negative 2, and there's no other computations, and this is a fraction we can't simplify, so our final answer is just negative 5 halves. Thanks for watching.